Welcome to the fourth lecture of week 3 of course Unit Operations of Particulate Matter. In this lecture we will discuss gas fluidization. Now here this lecture is divided into two parts, lecture 4 and lecture 5. In both lecture we will discuss gas fluidization. However, in lecture 4 we will discuss the classification of powders and how these powder behave in fluidization environment, that we will discuss. Whereas in fifth lecture we will discuss the entrainment, how the entrainment is counted in fluidization process, and then design of fluidizer will be illustrated through an example, and then we will discuss application of fluidizer in industry. So let us start the fourth lecture, which is on gas fluidization. Here we are discussing non-bubbling fluidization as well as bubbling fluidization. You understand what is non-bubbling, which we have also called it particulate or homogeneous fluidization, and bubbling fluidization we call this aggregative or heterogeneous fluidization. Particulate fluidization as well as aggregative fluidization we have already discussed previously, but here these two will be discussed in terms of gas fluidization. So first we will discuss non-bubbling fluidization, which is nothing but the particulate fluidization, and you understand what is particulate fluidization is where the particles are uniformly distributed in the bed. So let us start with non-bubbling fluidization. Although fine particles generally form fluidized beds more readily than coarse particles, the surface related forces tend to predominate with very fine particles. So here you see, though fine particles are fluidized easily in comparison to coarse particle, but it has some problem as far as fluidization is concerned because of surface related forces acting on fine particles. So it is very difficult to fluidize some very fine particles, as they tend to form large stable agglomerates that are almost entirely bypassed by the gas. So here what happens when we are considering very fine particles, due to surface related forces they join other particles and prepare a bigger particle. So when particle will be larger, the gas, instead of making it fluidize, it bypass these particles. So that is the problem with very fine particles. In some extreme cases, particularly with small diameter beds, the whole of the particulate mass may be lifted as a solid piston. So here when we are considering very fine particles, sometimes this situation occurs that instead of fluidizing a single particle or fluidizing the particles, the group of particles, what happens, all fine particles join together, and when it is fluidized, it's the whole section is fluidized once, so that will be lifted as a piston. So at low gas rates, the bed may exhibit a regular expansion as the flow rate increases, with the following relation between fluidizing velocity and voidage. So what happens when we are considering non-bubbling fluidization or particulate fluidization, regular expansion is observed at very low flow rate when we are dealing with the gas, and as velocity increases, the following relation, this is UC by UI is equal to e raised power n, it speaks about how voidage will be related to the velocity. Although in general the values of exponent n, that is if you see this expression, here we have e raised power n, so n are higher than those for liquid solid system, because particles have a tendency to form small agglomerates, thereby increasing the effective particle size. So here you see, when we have we are dealing with the gas at low flow rate, bed expansion will be uniform, and that can be correlated with the voidage by the expression UC by UI equal to e raised power n, but here n value should be larger in comparison to liquid fluidization. Now we are discussing bubbling fluidization, where The region of particulate fluidization usually comes to an abrupt end as gas velocity is increased. So, in bubbling fluidization what happens? Bubbles formed inside the bed, and that happens when particulate fluidization comes to an end. These bubbles, which are formed after particulate fluidization, are usually responsible for the flow of almost all of the gas in excess of that flowing at minimum fluidizing velocity. If bed expansion has occurred before bubbling commences, the excess gas will be transferred to the bubbles whilst the continuous phase reverts to its voidage at minimum fluidizing velocity, and in this way it contracts. So, here what happens when we are dealing with bubbling fluidization, how the bubbles are formed when we are having a fluidized bed, and when gas velocity increases, then after achieving minimum fluidizing velocity, if gas pass through the bed with higher velocity than that, so instead of expansion of bed, that gas is accumulated as a bubble, and that bubble will keep on increasing when we are moving from low bottom of the bed to the higher side. And the continuous phase where particles are available, that comes down. So, that section is that section where particles are available, it contracts, whereas the other section have forming of other section has different bubbles. So, the main point is particulate fluidization stops, aggregative fluidization starts. So, in the case of gas fluidization, what happens? At low flow rate particulate fluidization proceeds, whereas when velocity increases, it converts into the aggregative fluidization, and the formation of bubbles occur when we are having excess air in the bed. So, upper limit of gas velocity for particulate expansion is termed as minimum bubbling velocity. Here we have understood that once particulate fluidization will occur, and after that aggregative fluidization will occur, and therefore we can say that bubble formation is occurring in aggregative fluidization, and therefore we can say the minimum velocity of gas where bubble will be formed, that will be the highest velocity where particulate fluidization occur. And in this slide we will classify different powders. Now, why we are classifying? Because each powder has different tendency, different particle size. So, how these powder behave with the fluidized environment, how these powder behave in fluidization environment, that we have to observe. So, the ease with which a powder can be fluidized by a gas is highly dependent on the property of particles. In general, fine low density particles fluidize more evenly than large dense one, provided that they are not so small that they make agglomerates. So, here we have different powder, and each powder has different category because it has different property, and they behave differently during fluidization. For example, spherical particle fluidized easily. In this respect, long needle shaped particles are most difficult to fluidize. So, particles of mixed sizes will usually fluidize more evenly than those of uniform sizes. So, here we should also understand that it depends on the shape of the particle, like when spherical particle we are considering, it will fluidize easily, whereas if it is needle type or strip type particle, it will not fluidize easily. And when we are considering mixture of particles, where different shapes are available, so that can be those particles will be fluidized evenly in comparison to uniform particles. So, now we will discuss the classification of powders. Geldart classified powders into 4 groups according to their fluidization property at ambient condition. Geldart classification of powders is now used widely in all fields of powder technology. So, here we have 4 group. Group A, powder, when fluidized by air at ambient condition, give a region of non-bubbling fluidization beginning at UMF. Now, what is UMF? Is minimum fluidizing velocity. So, the powder falling in group A, that shows particulate fluidization when minimum fluidization condition will be achieved, and further bubbling fluidization occur when velocity increases. Group B powder give only bubbling fluidization condition under ambient conditions. So, you see here we have group A where bubbling as well as non-bubbling fluidization both will occur, whereas in group B only bubbling fluidization occur under ambient condition. Group C powders, these are very fine cohesive powders which are incapable of fluidization in a strict sense. So, you see when we are considering group A, it has initially non-bubbling fluidization, then bubbling fluidization. Group B, it is started with bubbling fluidization. Group C, it is very difficult to fluidize the powder which are falling in group C. Now, we have group D powder. These are large particles that are distinguished by their ability to produce deep spouting bed. So, group D powder has a tendency to prepare to make the spouting bed. Now, what is a spouting bed, that we will discuss in subsequent slides. Now, as far as classification of powder is concerned, here we have 4 groups, and now we will see the effect of parameter on behavior of these powders. Here we have Geldart classification of powders, group C, A, B and D. Here you see the first point is most obvious characteristic. What is the most obvious characteristics of these powder? Group C, if we are considering, these are cohesive and very difficult to fluidize. Group A, ideal for fluidization, exhibits range of non-bubbling fluidization. So, group A has initially non-bubbling fluidization, then bubbling fluidization. When we are considering group B, it has bubbling fluidization, but that will be started at minimum fluidization velocity, and that will be started once minimum fluidization condition will be achieved. And further, group D, these are coarse solid. So, particle size are large in group D, and similarly we have other properties. For example, if we consider bed expansion, group C, low because of channeling. So, what happens when we consider group C powder, because these are very difficult to fluidize. So, gas which is used to fluidize these powder, that passes the powder without fluidizing it, so that forms a channel inside the bed. Group A, that is ideal for fluidization, so obviously bed expansion would be higher in that case. Group B, as it is having bubbling condition, bubbling fluidization occurs over here, so bed expansion is not that much high, it is moderate. Whereas in group D, where we are considering large particle and spouting bed are formed, their bed expansion is very low. So, similarly other parameters you can study for these 4 groups of powder. Now, how we can calculate the minimum bubbling velocity for different condition? So, the superficial gas velocity at which bubbles first appear is known as minimum bubbling velocity. Abrahamson and Geldart correlated the maximum value of UMB with gas and particle property using the following correlation, where UMB, that is minimum bubbling velocity, is equal to 2.07 exponential 0.716 f into xp rho g power 0.06 by mu power 0.347. Now, in this expression, xp is mean sieve size of the powder. We have to first carry out the particle size analysis we should first carry out the particle size analysis to know what is the mean size available in powder, and in this expression F is the mass fraction of powder less than 45 micrometer. So what is F? Here we have different sizes of particle in the powder, and the fraction of particles which are lesser than 45 micrometer, that we have to consider as F. So considering this expression, we can calculate minimum bubbling velocity. Now what happens in group A? Group A powders where UMB is greater than UMF. Group A powder, what is this powder? This is ideal for fluidization, and in this case minimum bubbling velocity should be greater than minimum fluidizing velocity, and at this condition bubbles are constantly splitting and coalescing. This makes smooth fluidization. So if you see this figure, here we have splitting of bubble and these bubbles are joining, so coalescence will occur over here. So splitting and coalescence occur simultaneously in this bed. So through splitting and coalescence, bubbles achieve a maximum stable size, effectively independent of gas velocity or vessel size. So when bubbles are formed, these are continuously broken as well as join other bubbles to make a larger bubble. So this happen in group A. So you see in this slide, I have shown two video. In video 1, if you see this video, here we have non-bubbling expansion of fluidized bed of group A particle. Here we have non-bubbling expansion of a fluidized bed of group A powder. Now if you observe this video, what happens? The bed is continuously moving. It means all particles are continuously moving in this, and the uniformity we can easily observed over here. Whereas when we are considering this video where bubbling fluidization occur of group A powder, here you see bubbles are formed, and when we observe these bubble size will keep on increasing when it is moving from bottom to top. So in this way the bubble bypass the solid and fluidization will not occur properly. And when we consider group B, as we know that in group B only bubbling fluidization occur. So when minimum bubbling velocity is equal to minimum fluidization velocity, bubbles continue to grow in size, never achieving a maximum size. This makes for rather poor quality fluidization since there are large pressure fluctuation. So what happens when you observe this video, here though granulars are there, but when gas enters into this, it enters in the form of bubble. Now when gas enters into this, it forms bubble, and these bubble will keep on increasing its size till it move from bottom to top, and at the top eruption of bubble occur, and due to this it carries some solid particle, but it will be again fall down in the bed, as you can observe here. So this video shows the continual increase in size of bubble in a two-dimensional fluidized bed of a group B powder. Bubbles increase in size with distance from the distributor and with increasing gas velocity. Bubble size is limited only by the vessel size. So bubble size will be dependent on the diameter of column. It cannot be larger, so it is only dependent on the column diameter. Now when we consider group C powder, we have discussed that in group C powder fluidization is very difficult to achieve, and that we can easily observe through this slide. Now in this slide I have shown this video. So what happens in this video when gas starts passing it, you see there is no fluidization occurring, the particle will not start moving. However, after some time the block of particle will move upward through the gas. So, gas will carry not a single particle, not a number of particle, but the bulk of particles, or we can say it will let the powder move in the form of piston, and then it breaks down, and then after some time channeling occurs inside this. So, what happens? So, in group C powder, the interrelated particle forces are large compared to inertial forces on the particle, and as a result true fluidization does not occur. So, that is a tendency with group C powder particle, that the interrelated forces are very high. So, these are connected to each other very tightly, and therefore it is very difficult to fluidize. Bubble as such do not appear, instead the gas flow forms channels through the powder, as we have already discussed. Now, there is another problem with gas fluidization, that it has the problem of slugging. Now, what is slugging? When the size of bubble is greater than about 1/3 of the diameter of the equipment, their rise velocity is controlled by the equipment and they become slugs of gases. So, if you see this video here, what happens, granulars are there, and due to formation of bubbles, instead of movement of particle, the bulk of particle move together, and if you see the size of bubble is equal to the diameter of column, and then after some time it falls back. So, this is nothing but the slugging. So, slugging is attained by large pressure fluctuation, and so it is generally avoided to large unit, since it can cause vibration to the plant, and similarly you can observe slugging in this video. Now, here we have spouted bed, as we have discussed that the powder falling in group D, they behave as spouted bed. Now, what is spouted bed? The spouted bed represents the ultimate in channeling. The spouted bed represents the ultimate in channeling in a fluidized bed. Gas enters at the conical base, with much of it flowing rapidly upwards through a center core, and the remainder percolating through the surrounding solid, which may not be in a fluidized state. So, what happens in spouted bed? When gas enters into this, it forms a channel in between, and the particles which are falling in this channel, they rises and then they fall to other side. However, the particle which are not falling in the path of gas, they remain as it is. So, in this way spout forms in fluidized bed. The solids therefore form a wall for a central spout of gas, gradually become entrained and then disengage from the gas stream in a space above the bed, where gas velocity falls as the flow area increases from the spout area to the vessel cross sectional area. So, what happens when we are considering spouting gas velocity? Gas passes through a channel in between. So, when the channel is of smaller diameter, velocity will increase. However, when it reach to upper level, of the bed, it come across with larger diameter of the column, and then velocity decrease suddenly, and then therefore it carries the particle, they fall suddenly to the bed. So, you can observe a spouting bed in this video, where gas passes over here, where gas passes from the bottom and it forms the channel. So, you see other particle which are not falling in the path of the gas, they maintain uniform height of the bed. So, you see particle which are available in channel, they rises and then they fall, because when gas reaches at this point, it come across with larger cross sectional area, and therefore its velocity decreases suddenly and the particle fall. So, the spouted bed fluidizers are used as efficient dryers for drying seeds such as rice and wheat from high moisture content, that is 20 to 25 weight percent, to medium moisture content, that is 18%. So, in this lecture 4 we have discussed different types of powder, we have discussed different conditions which are occurring in these powders, and here we are stopping this lecture. We will continue gas fluidization in next lecture. So, that is all for now. Thank you.